but then sort of Shella and Petra both kind of went through certain parts of it. I think she showed a nice diagram that only 5% of the energy is used for task, like 20% for rest. And even Petra showed all these big traveling waves. So the question is, where's the task and what is this activity and how do we make sense of it? And so there has been some really nice previous work by Cole and Ito in 2016, where they have showed sort of that if you take sort of weighted components of the functional connectivity, you can start of the resting state functional connectivity, you can get to the task functional connectivity. And then there was another work by Tan, which does the same thing, but using sort of DTI networks. So there's this idea of these sort of subcomponents of rest being used for task. And basically, I'm going to show this using ODEs, where we show that sort of these task ODEs are a subset of REST ODEs. And so the talk's basically in two parts. The part one is how do we create these ODEs for sort of these data, fMRI data. I use a data-driven approach, which I'll get into real quickly. And then the second part is how do we investigate how these ODEs are related to each other. So how do we fit an ODE to fMRI? I use a technique pioneered by Brunton called sparse identification of nonlinear dynamics. The idea there is to solve in the derivative space x dot equal to f of x, and you just create a Taylor series polynomial to represent f. And oops, no, that's not what I want. That's what I want. So what we do here is we have sort of nodal dynamics that we've made really simple, that we're just sort of going to constrain as this negative lambda term, which is just an exponential decay from the HRF. And then we're going to solve the network terms. And you need these constraints here because without it, you don't really get any realistic solutions. And there's a lot of functions that fit fMRI data. So constraining things, especially in a data-driven approach, I think is very important to get realistic answers. How this looks is once you fit your sort of network model, you can take the sort of the measured derivative, subtract the network derivative, and you can see that what you're left with looks very uncorrelated. This is just regression. You put everything that you know into the structure and everything left over should be noise. So this is just regression doing things correctly. When you look at the coefficients of what these Taylor series polynomials, they look like, is you can, for each polynomial order, you can take the structure of it and we can compare it to the sort of measured network from DTI. And we can see that for odd order of coefficients, they're very highly correlated, especially for the intra-hemispheric edges, so the connections within one hemisphere. There was this really nice talk a couple hours earlier that was talking about sort of this inhibitory inter-hemispheric edges. And I kind of see that too in my sort of my connectivity that I get here is I get very strong contralateral edges between two hemispherical twins, but then you kind of have this sort of inhibition coming from the other hemisphere to the neighbors of your twin. So I see this really nice structure. The edges, when you actually look at the whole function, because they're all odd polynomial, you get a nice sigmoidal shape. So putting it all sort of together, I made the picture look a little simple. It's a little bit more complicated. To really get a proper network model, you have to sort of deal with the structure dynamic tension. And this is a classic sort of sparsity thing that we have. You can have networks where you have many edges, then you fit the dynamics really well, but then your correlation to your DTI drops really low. And then you have networks where if you increase the sparsity, you have only few edges, and then the correlation to your DTI gets really, really high, but then you have no connection to the dynamics. Luckily, you can also throw in these constraints for the HRF. And so when you sort of put everything together, we drew this purple line of these sort of models that have enough of a threshold of these, and then we use these forward into understanding the fMRI data. So this sort of concludes part one. This is how we generated these ODE models for rest and task epoch. They're completely trained on the data that you give it to them. So you get different ODEs for what data you put in. So we trained 5 different ODEs: rest, emotional, gambling, working memory, relational, from HCP data. And the result that I'm going to show here is that these task ODEs are really just subsets of these rest ODEs. And so I want you to consider, sort of going forward, 3 sort of separation frameworks. The first one, I think, is the one that we're most sort of familiar with, is this idea of what I call the rest baseline model, is that the measured activity we have is the rest network activity. So maybe something like, these big, giant, swirling patterns, and then everything else corresponds to what we're actually processing. So the stimulus is nothing but you just take the measured activity, subtract the rest network. You can also do a task baseline model, which is the same thing, but you're just using the task ODE. And then what I actually end up showing, which I didn't actually understand for a very long time, is this active cortex model, where actually the stimulus couples with a portion of these resting state networks. And then the coupling is actually the task ODE that you trained from. And so the stimulus or the task activity that we really want is the measured signal minus the rest ODE, so the big pink, but then you add back this little slice here. And when you do that, I'm going to call this the sort of the separated signal. You focus in on just the task signal without any of these giant resting state cortical activity. So we're going to test which of these frameworks suits the data best. And we're going to do this in 5 different behavioral measures. I only show 2 here. The rest are in the paper. And yes, so quickly, how we sort of chop up the task is we align at each stimulus onset from HCP. We cut sort of 14 seconds. And then we have a reaction time for each of these. And we also have the accuracy and which ones were missing trials. They didn't do it. And then what we're going to do is we're going to construct this sort of function here for the new activity without the components of either the rest ODE, which is just a giant equation, or the task ODE, which is another giant equation, both of them that we use regression to find. And here, very general, we're just going to put in these coefficients, and we're going to manipulate a real signal. And then whatever our separated signal is, we're going to then correlate it with the behavioral measures. And so we needed to do another brain to behavior function. We did this in 2 different ways. We used just simple correlation. The second one, we built an entire elastic net that sort of takes all of this information and then summarizes it into one value, which we can then compare with the reaction time. So here on the top, we have sort of the results of the max ROI correlation for the 3 sort of big frameworks: the task baseline, the rest baseline, the active cortex, and also the unseparated case. The active cortex is the only one that does better than the unseparated, and it's significant in 11 of the 14 tasks. And if you sort of accumulate all of the activity across all ROIs, you get our elastic net prediction, where you see an R-squared increase of around roughly 10% across the 14 subtasks. So the active cortex is much better at localizing task-specific activity. And so let's generalize this a little bit further. I here tried a linear combination of rest and task. So this is the first step. I think the reviewers wanted more complicated nonlinear combinations, but for the first step, we're just taking sort of linear combinations of rest and task. So when one of these coefficients is 0, that's just sort of the horizontal lines here. So there's the rest baseline and the task baseline. And the color shows how much increase of correlation from the unseparated case you have. And you can see that for working memory, yeah, it's all wrong. The diagonal for emotions a little off. Relational also does great. And then gambling, I think, is a terrible task, and they should have never included an HCP. Sorry about that. But you can see that in the trend, it's mostly, really, you have to sort of you remove all of these baseline processes, and then you add in the ones that are specific to your particular task. Another way of sort of visualizing it is using sort of the functional connectivity. So rather than just using reaction time here, we take each dot here represents the functional connectivity of the entire task signal when it's unseparated, or when you apply the different frameworks for rest baseline and task baseline. And you can see that from this Venn diagram, you're basically trying to remove the sort of the overlap to push these two task separations apart. And when you apply the active cortex in this beautiful UMAP, you can see finally the colors all separating as these tasks are, the common processes in these tasks are removed and the tasks themselves sort of come out. And another reviewer comment, which I had to deal with, which was difficult, was are these just, random button pushing, or, is there some real sort of deeper science going on here? And so I really like this idea. So if you look at task severity, so not just what regions activate during the task, because that could be motor or whatever, because you had to press a button. But if you look at harder versus easier tasks, you find the brain areas that are sort of more responsible for the increased load in cognition. And those regions in increased cognition matches the areas that are driving this increase in correlation between the brain signal and the task performance. So this removing of these processes is highlighting the parts that we know already are responsible for processing these tasks. This is it for working memory. In conclusion, we constructed, using regression, viable ODEs for rest and task. And we showed that sort of this active cortex model, where the cortex is always active, but then during a certain task, certain parts of it are elevated, allows for separating sort of this unrelated network activity from the task activity. And it's a very general approach. This can be used for pretty much any task you want. I think it's going to be a great sort of technique that other people can, if they want to understand more things, can use. There is a sort of a caveat here that you do need some amount of large amounts of fMRI data for these models to converge. Yes. And thank you everybody in Berlin and Atlanta for helping me through this process. Questions?